Hello, well, today is June 23rd, 2023, and good evening. What we've been talking about here is mostly about the differential analysis and kind of that being the whole field of the realm of analysis writ large. So analysis writ large is basically figuring out anything with mathematics. Dynamical modeling is basically figuring it out anything in mathematics according to time. And then there's physics. It's got the physical interpretation with regards to models, model theory. Model theory is basically our fundament for what, with regards to the descriptions of things that we have axiomatic set theory way down below, and above all that is descriptive set theory, which is model theory of sorts, and it comprises these kinds of fields of arithmetic and algebra, and number theory and geometry, according to geometries fundamentally relations of topology and function theory, the theory of the functions or relations. So in this manner, there's been discussion over time of the descriptive differential dynamics, and what does that to mean? Well, the descriptive differential dynamics is basically what the dynamics are, those things that affect and reflect each other and change, and how they're still related as their relations change. And then what has been kind of a topic of the study or the discussion has been what are those things that are the extremes or the asymptotes, which make that in the analysis they become these points of singularities, where really the definition of a singularity is a multiplicity. That otherwise in these operations, according to that the operator calculus is a very tractable milieu for manners of manipulation of systems of equations up above, kind of, that the operators are closed usually, and that's really a key thing because it indicates for each previous annexed, for each one and other, a distinct and unique other. Then the idea of the multiplicity is anything to do with a one-to-many. In usual cases, reduced to branching, 1 to 2, but 1 to any, 1 to many. And then the most familiar notions of those to people are division by 0, undefined. Maybe it's infinity. Or the root with respect to a negative number, an imaginary number, I, the square root of -1. And they regard that as positive and negative roots both exist. An example of multiplicity, that when infinity closes division to division by 0, that's a little bit different of a thing, but it could be related to it could be infinity to infinity, 3 infinity, in terms of that it's those quantities connected according to the algebra where it's kind of either unelementary, it's molecular, say, or combined as in terms of the atoms of the algebra, or that it's degenerate and it's actually the quantities are in as of underneath, that they define the quantity and an associated quantity, these kinds of things. Now, of course, the more sensible and tractable, sensible and fungible and tractable here being the desiderata and requirements of methods and analysis, is the linear and the closed and the classical. So here a large focus of the interest is the superclassical, and in a sense that's retro-superclassical. When we talk about Aristotle's continuum, it's these same iota values between 0 and 1, constant difference in infinitesimals, as since Aristotle, for example, or for Zeno's arguments, providing a framework where the limit is the sum in the completion in this higher order framework. That then there's just a general course of studying the linear analysis and in the differential equations and the systems of equations that so result. It's very closely related with vector algebra and vector spaces and the linear systems and matrix methods. That a matrix is basically a way to take for a system of equations in n many variables, n many equations or so, or an m by n matrix, or as it may be, according to a convention of height and width of the matrix, that then for each of those there can be placed in it usual values of these things. And then there's very well known means of solving for systems of equations and equations and unknowns, as it were, to be able to find out whether it's possible to find equations in those via echelon rank reduction or Gaussian elimination. But otherwise, as a usual exercise in solving for variables and systems of equations, that the linear is very well understood, and its methods are very well regular, and their bounds of what it takes to write them out and write them down and crunch them out and crunch them down and get the numbers out are very well understood, and the time and space complexity of those terms is in well understood combinatorics of the terms. The nonlinear, though, at the same time that it's not necessarily so tractable, that at the same time there are such closed formulas as represent what for it are more sensible, fungible, and tractable, basically according to roots and powers, exponents and logs, and for example, the methods of trigonometry, according to properties of functions about trigonometric or the hyperbolic trigonometric, or otherwise geometry of circles is nonlinear. Fundamentally, the nonlinear is a circular, and when it angular is the nonlinear, and so the linear is the linear, and the rotational and the angular is the nonlinear part to be described and get figured out. So in all such manners of things like periodic wave motion and representations of oscillations, then with regards to things like classical motion, and basically there's always classical motion in time is the idea, and that fundamentally results again being back in analysis, in dynamical analysis and dynamical modeling. The idea is the entire universe is one big equation governed by time, and the space and time that exists, and according, of course, to all that already exists. The past already exists and is written. The future is not yet written. So anyways, every couple days I try to go to one of the local bookstores and see if I can find new books. So I often do. And generally I look for books that have a certain historical meaning, or with particular relevance that they've survived. And so that includes stuff like literature. I mean, I do read some fiction, though largely I stopped reading fiction after basically my 20s. I stopped reading fictions for fiction's sake. And I still enjoy it, as it were, but not so much. So, and then in terms of the nonfiction, there's basically classics, and classics is generally refers to antiquity, and then there's the Enlightenment age, and the canon, the canonry is all that kind of stuff, and I like to become familiar with that as a historian of sort. A researcher in foundations has to know these kinds of things, or else they wouldn't know these kinds of things. And well, at the same time, though, as simple an introduction to the dialectic and the square of opposition and such, and deduction is familiar from anybody who builds rules to describe their reality. It's called science, and anybody who practices logic and rational, reasonable inference does it. That at the same time, there's this body of work that describes then, in reflecting the schools of men and women, schools of people collectively, but schools of men, over time, and their changes over time, and their comings and goings when the cycles come around. There's a cyclic histories where what's happened before has kind of happened again, and that these then advise us on what to look for in these things that are relevant. And so I'm always looking for something that's classical, or I'm looking for modern compendiums of the sorts. The other day I was reading this Russell and Norvig's Artificial Intelligence, and it's a pretty good book. It's a compendium of all kinds of historical settings of this relatively new field called machine learning or artificial intelligence and that kind of stuff. And it helps reflect, with the study of after the invention of computers, which can be pointed back a long ways, the notions of the existence of computers or things that are mechanical, that compute information, or the mechanical generally. that then there's also the notions of what is the representations of knowledge. And that these days a lot of it is like these neural nets and vector space models, and I don't really see those as very well founded. That they're mostly, from my perspective of them, my tripos of artificial intelligence being expert systems, machine learning, and statistical inference, that almost all of them are kind of a particular funneled machine learning into the neural nets and Markov models and such. And what factors in relations kind of go into the same thing, where this differential analysis is largely geared towards arriving somewhere where the computer can take over and crunch out a number. All you have to do is pose the problem well, according to Hadamard, who I was reading about a little bit, and then the linear analysis is gratis in a sense. So it's kind of similar to some of the things like the supervised and unsupervised classifiers and learning and this kind of stuff, according to what is feedback loops and reward functions and these kinds of things. That I when I say I don't find it as well, if we're very well founded, it is that my ontological domain is much more than less based on knowledge and science. And insofar as that may well be implemented in sorts of manners of facts of abstracts, these objects in the brain, that it's a highly connected neural net, as it were. That at the same time, the overall approach to the methodology and the ontology is that it is an ontology, and so on and so forth. And then as well, there's descriptions of fundamentally theorem proving or fact correlation. And so in studying these kinds of fields, then one thing about that is such a compendium as this 800 pages or so of 14 or 20 chapters of each one about a segment of the development in the history of the field, industrially and academically and amateurly, the artificial intelligence, that it's mechanical thinking. So as far as that goes, intelligence, there's mechanical thinking, and then this other stuff is just large, scaled out, highly capitalized and capital intensive things that more than less reflect that it's not that AI is hard, it's that AI is easy. So one hopes that will see developments that make it so that we're more than less well advised in terms of what decision-making support, where decision-making support is a big aspect of dynamical analysis, decision support and operations research and decision support, ends up being well advised in terms of what tools we use and knowing where the food comes from, as it were, and chewing the food. Always chew the food. And it reminds me of another book that was really good. There's one called Algorithms and Data Structures. So this is basically an MIT textbook. It's a freshman textbook for computer science students. And what's in it is all these usual algorithms on usual data structures that everybody will know and are implemented in all the standard libraries of all the language of the computer programming. Lists and queues and vectors and maps and associative arrays and getting up into graphs and these kinds of things. And then there's something like Knuth's The Art of Computer Programming, volumes 1, 2, and 3. These go a long way not only into the algorithms that are presented, but the analysis of the algorithms in terms of their runtime. There's two runtimes, two resources in runtime, time and space. And then that resolves it. There's one resource in runtime, which is time. And then in some sense, that's variously interpreted in terms of money, in terms of either watts or time. And then it's all one distributed system, which is called systems programming. System theory. Then there's the idea that physics, basically, when we talk about physics as a system, that physics as a closed system is kind of like these models of the heat equation that we've been talking about, that the physics as a closed system is when there's no interpretation of any other mathematical model at all than the physical model. But physics is an open system. Some mathematical objects, like when they're closed by their operators and stuff, that's the same kind of thing when you say they're open or closed by their operators upon them, and the effects and the causality of effects from first principles to final causes, this being the entire range of why anything happens, answering any question word, that not that we know what they are, but that's the definition of what they are. That this is the kind of thing that goes in the thing. So anyways, the other day I was trying to understand a little bit more about the geometric mean and the arithmetic mean and the harmonic mean. And so these are different ways to describe the midpoints or the intermediate parts between values and how they interrange. Most people are familiar with the curve is any kind of straight or smooth curvy curve, and then the tangent line is that at any point on a curve there's exactly one line in that same plane or the curve lives in a surface, that in that surface there's exactly one line that crosses it, or one subsurface that crosses it. Here, when I generally describe a curve, it will be just a line, whereas then its surface is basically a collection of lines. Each curve is one way to look at it. Variously about how then that is also considered. Thinking back into about 20 talks ago, there was quite a big thing going into that the tangent line is otherwise represents in the space where that curve lives, where the function or the curve lives, the instantaneous or exactly what would be incident to this thing. There's the tangent, and then there's the normal as perpendicular to that in the same surface, on the same surface, and so on. So the means are in as between those. Now, before we get started on geometric, harmonic, and our arithmetic means, then basically the average is the arithmetic mean. And so the mean, median, and mode is the arithmetic mean, and it's in terms of samples, then that the mean is the average of all the samples. The median is out of all the samples in an order, the one in the middle. And the mode is the sample with the most samples. That's like the discrete side, where then these other means get into the continuous side. Okay. The average or arithmetic mean is in both. And so about that reference to the backstory, there's discussed what is basically this notion of the Laplacian. Now, the Laplacian is in terms of the partial derivatives. So when we're talking about that the curve is, for example, a surface is all these curves in a parallel array. The manifold, a surface in 3 dimensions that has 2 dimensions, i.e. that there's a mapping between that preserves locally all these orthogonality and proportionate form as if it were flattened. Okay. So anyways, the idea is then in the Cartesian space, that's in terms of triangulation or coordinatization in terms of orthogonal vector bases, or otherwise in the coordinate setting, that there's more than one ordinate, that where that function, it lives in that space, that it drops to the line on that ordinate, as if you were to connect that point via a perpendicular to the axis of the coordinates. That's its ordinate, and the abscissa is like what draws across that. So the abscissa and the ordinate are these terms where the pieces fit in there. That's where they, if you were looking from only that side of that box, that's what would be projected to. So these are descriptive terms, and they apply to anything that have these kinds of properties, and they're just like so. So anyways, the partial derivative is looking from one side of the box and then looking from the other side of the box. through the faces of the cube, say, in the orthonormal Cartesian space. And then the idea is that then those together basically have that if they're both zero, then it's a minimum in a sense. It's not going up in one or the other directions right there. But you can still imagine how, if you were to look through the corner of the box, you can imagine an arbitrarily contrived shape like the saddle, or sometimes they have that, and this is in topology, they get into these various shapes that are these curves, so for these surfaces, they define where they, in methods like the Laplacian, no longer become well posed in the Hadamard sense. The other day there was a brand new paper out from somewhere, and it studied, they have a notion like the swallowtail. And so it reflects a kind of bird, and in the shape of the fan of his tail, it came out. But they did a particular study around its fan, and what they were able to figure out is something along the lines of one of these multiplicities. They're like, wow, it's multiplicity theory. Well, yeah, it is. And then they were able to find a method that then they were able to translate into a linear system, and surprise, surprise, they were able to solve some things that before were iffy. So the idea is that this linear analysis has its, by the same time it has its completions, it has this incompleteness, or is in the asymptotic. And so the idea is to figure out how to translate or transform the image or the perspective of the curve. So there's something like the hyperboloid, which is 1 over x, and that's basically as well a conic section. And though this is touching a lot of different definitions, they all live in the same space, and they always all have the same definitions throughout the entire space of the geometry and the space of these terms. That trying to figure out how to get those attached together so that then when some of these methods of sensibility and fungibility and tractability can be applied, that it's possible to get a lever or otherwise a hook into the thing and be able to reel it in a sense, or to move it. So these are the kinds of things that were going on. So I got another book, and what is it? It's Geometric Inequalities. And so the idea is that inequalities are most familiarized from arithmetic, and they're one of the first concepts learned in the representation of arithmetic quantities. Right after the numbers are defined in counting, and there's the operations, addition and subtraction and multiplication and division, the usual arithmetic operations that powers and roots are kind of following on after those. And logs and exponents are as well. One way to look at that is that you just start with increment, and then you get to addition, and then you get to multiplication, and then you get to powers, and then you get to exponents. Well, at the same time, then they're written that way, they scale out in terms of this geometry. Still, one of the most amusing things that I'm still trying to figure out is the quadratic sieve. Draw a parabola, y equals x squared, on an integer lattice. For each integer point, which is where there's no non-integer part of the point on the parabola, connected via straight line to each other integer point on the opposite side of the parabola. So it's a U or V shape. And then each of that 1 and 2, 4 and 3, 9 and ... they're all integer points. And so you connect them, and they cross all the composite numbers and all the integer points on the axis. All the ones that are composite are crossed, and all the ones that are not, that are prime, are not. I'd like to figure that out because for a couple reasons. About the fundamental theorem of arithmetic that numbers have prime factorizations, and about how that's so just from drawing the y equals x squared, that function, and connecting the dots. So anyways, this after arithmetic, there's inequalities. And so this is the difference between equals and not equals. And so equals is basically most familiar probably from childhood. There was a television show, and they had one of these things is not like the other, and they would box the screen on the show into 4 sections, and then they would show 4 different activities, and 3 of them were the same kind of activity, and one was kind of different. And then they say one of these things is not like the other. And so how that relates into mathematics basically is one of the very strong rules that ends up being everywhere. It's called triangle inequality. And that's basically that only in this quadrant are things like the other, and everything else could fall out because it lives under the square. So from this preschool and elementary and kindergarten and elementary beginning, then we get into inequalities, greater than or less than. These are familiar as the caret signs. They're called angle bracket. Left angle bracket, right angle bracket is their names. And they're also called just greater than and less than. And when you put them together with equals, then they combine greater than equals or less than equals. GT and LT, GTE and LTE are angle bracket and L angle bracket. So so those are introduced, and there's not introduced something like not equals. So the equals is just the equals bar. Sometimes you'll see the equals bar with a tilde on top. It means approximately equals. Sometimes you'll see the equals bar with 3 bars across. It means on the order of or via extensionality. These are various ways to write equality when it's really just that a relation is established. And in our arithmetization, we're using arithmetic. And as long as we use it according to the arithmetization, and you can treat it like numbers or quantities in algebra, it will hold. And then when it doesn't, you just make a stroke through it or strike through it, and then that makes a not equals. Not equals. So anyways, inequalities are key because you can define things in terms of, and many of these proofs are based on the fact that it's established, for example, delta epsilonics, there's arbitrarily small quantities, and it's used inequalities to establish that what is the vanishing of the difference from the limit and the sum, that the series has a limit. That's our standard formal way, vis-a-vis this super retro classical standard way where it is the sum, because it's no different from the sum. A usual argument for that is the limit from both sides not just is arbitrarily close, but they can't be any different, so they must share their same least upper bound. The limit is the sum. So anyways, that's the usual next step, and then it makes it clear that that's why it's well founded to be like so. Obviously, not all our derivations are built up that way. They're mostly built up going along straight, one-sided with the triangle inequality. And so this meeting in the middle of nowhere, is a well-established concept in these talks that's been coming up a lot. So then I want to learn about the geometric and harmonic mean. So this book, when I opened it up and looked at it a little bit, and it's from Andy Kazarinov from University of Michigan, from the Mathematical Association of America. And it was published about 1975. It's called The New Mathematical Library. Copyright 1961 by Yale University. So... And there's some other books in here I'll be curious to look at, like Uses of Infinity by Leo Zippin. I have not seen this before. I studied Hadamard a bit yesterday because I wanted to be sure I had a little bit of context in one that's called the well-posed problem. Well, the well-posed problem, the boundary value problem, basically is this sense, as was mentioned recently or just now, about that it stays amenable to these linear methods when it's possible to work out its solutions. That small changes in its initial values don't cause large changes in its values. And that used to be called chaos theory, but now it's all called dynamical modeling. And it's also called topology. There's a subfield of topology kind of about it, about the shapes of things, but it's algebraic geometry and also into the differential geometry here from the differential systems. So, looking around, it says this book is written by professional mathematicians for high school students and laymen. Cover topics, and so, but it has its first chapter is about geometric and harmonic means. Geometric inequalities are especially appealing because their statements can be easily grasped. And when it's geometric, also you can draw it out and you can see like it touches or it doesn't touch, it crosses or it doesn't cross. At the same time, they provide an excellent introduction to creative mathematical thought. So Hadamard, besides this, the well-posedness of boundary value problems, also wrote a pretty interesting paper that I haven't read yet, or book, and it was about the thought processes of mathematicians. And the way he described it is that he divided it into two kinds: people who think in words and people who think in shapes. I tend to think it's both, but the whole point of the descriptive is that there are symbols and words, and while that there's yet that geometry is perhaps the most proper of the mathematics. It's visualized in space. So, anyways, that gets into that one of the reasons that it's necessary to have such things as the rigorous fundamentals and axiomatics is because then that both kinds of thinkers are satisfied. It's the exact same reason why all students are instructed in phonics, so that any one of them can have that same fundamental tool to read any given word and then translate it into their acoustic and phonic model, mental model of words. It's for etymology, vis-a-vis recognition or that. It's kind of the difference between training an expert system with statistical inference and a neural net. You know, it's done in a way that makes it possible for everybody to learn the words. And then it's similar with instruction in terms of things that the linear curriculum, the whole point of linear curriculum, including stuff like arithmetic and equations and elementary algebra and geometry and shape sense and number sense and object sense, and then the timetables and computation and exercise, or sixth grade, and then is so that it's people with different learning styles will at least all have the same aspect. They say there's like a difference between a visual learner and a visual reader is that a visual learner can only learn graphically, but a visual reader is a speed reader. So anyways, historically, geometric problems involving maxima and minima were studied before the invention of the calculus. The calculus is a powerful machine by which one can solve some of these problems without ingenuity. It is not a panacea. A panacea is a pan, meaning all over, see a peacemaker of a sort. So it is not a panacea. However, anyone who intends to study or is now studying calculus will find the material in chapters 2 and 3 useful in understanding what the calculus can and cannot do. See here the author is reflecting on and representing that when to try and fold the whole field, including these issues and symmetries and submersions and sheaves, into descriptive differential dynamics, is that I've learned over a long time after the linear instructional curriculum and a major segment of that, and also personal researches and studies and and another major section, or having a whole mathematics degree from university, and calling that the first course in differential dynamics, that I've learned that a lot of these things that come into how, while at the same time they're stood up as like, this is how we solve it, this is how it's done. And then, you know, after I got at something like the table of integral series and products, tables of integral series and products, or Gradshteyn and Ryzhik, or something like the Handbook of Mathematical Functions, what's called Abramowitz and Stegun, that these books from the Chemical Rubber Company Press and printed by the government are National Institute of Standards and Technology, or Science and Technology, or it used to be Bureau of Weights and Measures. Anyways, the Handbook of Mathematical Functions, then Table of Integral Series of Products, really opened up my eyes to that there were so many extensions and cases in these special functions, to know that the reason those things are provided is because without that kind of lookup, and each one of those being a hard-earned result of major study in the differential calculus, that it would seem kind of a wash. It would seem kind of that there's not much tractability or fungibility in what there was. It's so this is sensible. So and then what I want to learn is how can I try and fold that up, because I cannot fit all this table of integral series of products in my mind. I do not know all the special functions. I want to know how they're related and for the fundamental and this kind of thing. That's really what I studied, to try and get, and sometimes those are the not intuitive results, but they can be most fruitful if it results that a true foundation is always true, and one of the most permanent and enduring things there could possibly be. So, the thorough reader must always work with pencil and paper in hand. I can't, I don't have time. I just need to end up with the least number of primitive fundamentals in mind and a working vocabulary for a working theory, that then I can relate how to start a problem and get into it and solve a problem. In terms of the thoroughness of reading. Now, it's fair to say here that this author reflects that it's important to take notes of something you're studying to aid in comprehension, and maybe that's particularly so when it's relevant to the style that makes for that the brain's proper resources are most aided by having a recent cache of the outputs and in a linear companion to the inputs. Maybe that's so, maybe that's not so for everybody. For something like this case, this is basically, all these talks are basically for me to learn how to talk about these things. That if you're to know something, you have to be able to explain it. And so entering into these sorts of didactic terms and pedantic terms makes it so that then it can be not just internalized and digested, or internalized and ignored, but internalized and externalized. That these are the kinds of things that get into what I feel is an exercise in learning. Then if there's any value of that for you to study this, is because I said so, but mostly because I know it as much as that. And insofar as that everybody's a mathematician, because they make do with the tools that they have. I make do with the tools that I have. There are the rest of them, and so anything you have that's right is right in all of them. Then the goal is consistency, completeness, and concreteness of a constancy. All right, anyways. So that's philosophical, but often drawing a portion of a figure in the text or rewriting a formula will clarify a troublesome point. Exercise and problems are important, and they reflect a lot of the thinking that goes on in the thing. So that's the preface. So now he begins. Arithmetic and geometric means. Let us consider with a straight line and choose a point O on it. So usually the origin O. Because of our experience with rulers, yardsticks, and measuring tapes, we can associate in our mind's eye matters of projection and perspective. This is why the fourth dimension is so utterly, it's not mentally realizable. It's not graphically, visually realizable to the usual apparatus after the eyeballs, which then behind them comprise the largest nerve bundle in the body, directly to the prefrontal cortex or the brain. And I don't know my atlas or topology of the brain so great, but I know that it's simple functional components. That the spatial hierarchy and organization is simply not that way. But we can draw on paper, and then how that's usually matters of projection and perspective. For example, anything you see on a screen, and your ability to interpret that as three-dimensional is also that three-dimensional is everybody's spatial, 2 and 3-dimensional. And 4-dimensional is difficult to visualize because it simply does not have one in regular space. What I do is just think of a formula called A plus B plus C plus D. And it's like, oh, that's 4 variables. It's like, well, yeah, as long as you treat it like a system of equations in a formula, then those are just variables. That's not so bad. It's the geometric and their relations and all these things that is cannot be drawn on paper and cannot be shown on the screen. So the idea is that then the projection and perspective of those, the ordinates and the abscissa here, or as from the partials, these ways, that's how they're visualized. We can associate in our mind's eye a number with each point on the line. A positive number if the point is to the right of O. A negative number if the point is to the left of O, and 0 if it is O. These numbers are called real numbers and may be written as decimals. So here, if you're familiar with replete real numbers with line continuity, signal continuity, and then field continuity, this is field continuity, and it's also geometries. And so most people will be familiar with this way. Thomas Hardy, first of all, they'd be familiar with geometries points, and that a line is defined in this way, and it is a continuous domain. And then with regards to point sets, of course, then that gets into arithmetic and the ability to write numbers as via the methods of Eudoxus. So all the way back 2,000 years ago, or in ancient Greeks, Eudoxus is who we call the field reals guy. You got Aristotle, kind of the line continuum guy, and you got Eudoxus, the field reals guy, and I'm not sure yet who to assign something like Nyquist and Shannon's signal reals to. And then those relate earlier in the prehistory all the way to the ancient Vedic and Sanskrit, which is called Anantas. Ananta was the patron of mathematics in the prehistoric Vedics, and about 6,000 years ago or more. And the notion is the spiral. The spiral is the symbol of mathematics historically. So anyways, Thomas Hardy, he was a mathematician. He wrote an apology for mathematics or something like that to help explain that he associates these real numbers on the line as the points on the line. And may be written as decimals, fractions, decimals. And they have infinite decimals after the radix or decimal point, as usual. The straight line we have associated with these numbers is called the real line. Sometimes as a vector space it's called R1. It's called one-dimensional space. It's called the real line. It's called a linear continuum. In pictures, we usually draw the real line horizontally and put positive numbers to the right of 0. Then he describes some numbers, and he says, all the numbers we shall be working with are real numbers. So that doesn't mean that all the numbers at play are not structures in these higher order surfaces. For example, a funnel that pours into a point is the funnel, besides a point. But as a real number, all you can really extrapolate, which is trying to figure out where a line came from, the opposite of triangulate, or just kind of extrapolate, interpolate, and extrapolate as antonyms of sorts, is the line where it came from, the principle of it, the principal component of its input, the mean, median, and mode of what it points at, of a sort. At this point, you have every right to object and say that we really have not defined a real number. This is correct. It is also true that a careful definition and discussion of real numbers is at the foundations of mathematical analysis. Such a discussion is too sophisticated to be presented here, but may be found, for example, in a course of pure mathematics by G.H. Hardy. So I just mentioned that book, and now he did too. Cambridge University Press, 1938. On the other hand, a thorough elementary treatment of some important properties of real numbers is given by Ivan Niven in Numbers, Rational and Irrational, another monograph in this series. I've not read that, so I will not vouch for its contents. I have my own theories about numbers that are dense in the real numbers, like this signal continuity, and about it. The rationals are huge in this kind. When we associate the real numbers with points on a straight line, we are implicitly asserting the real number system has certain properties. Since these properties are so fundamentally important, we call attention to them. First of all, we take for granted a set of all real numbers. There is a subset which is called the set of positive real numbers, and that this set, called P, has the following two properties. If A is a real number, then exactly one of the following statements is true. A is in P, negative A is in P, or A is 0. So this is kind of equivalent to a combination of that the reals are trichotomous, that greater than or less than or equals holds between any two real numbers, and so on transitively. A greater than B, greater than C means A greater than C. And here he's just describing that there's a partition. And so that's a way of looking at it. You can look at it various ways. When it's built up as about a combination of the properties, this is where the things in mathematics that are related, they're related by many, many properties. And the more central and primary the objects are, the more they relate the properties, and the more ways they can be written. And so when you get to a convention or something that has many, many other ways to write it, like Euler's formula or something like that, that becomes a narrow lane in terms of all the roads that lead to Rome or Denver these days, as it were. So that's just to say that now the author's established this particular property, and he's free to use it, and as long as he keeps it conscientiously the same throughout the remainder of the text. Also, it's true. If A and B are in P, then A plus B and A times P are in P. This is a usual consequence of what's the usual algebra structure called the field, and the closure of the operations of addition and multiplication. It's also that the vector field, the vector space, has so defined properties which basically reflect that in terms of multiplication by a scalar. So that it's a vector space, and the vector space's methods apply on it. There's these definitions, which are for the positive numbers. So he's calling the positive numbers P. This fits in our identity dimension as only the positive numbers. So this is just the positive x numbers, or R plus is another way to write that. And then when you notice that he starts with the real number line because everybody's familiar with it. That's probably one of the first and most familiar things to anybody when they talk about numbers, and their abstraction is the line and the numbers on it, and according to a measure 1.0, and that the least upper bound is fulfilled variously. And so while that's so, then it also reflects that he could just start with the origin and only the positive numbers, before I even got to that. And they say, yeah, and then later we can reflect that and talk about that being just like your lines. So you notice he's had to kind of restrict where he's coming from. But at the same time, that fundamentally could be the generator of the course of an expansion of a multiplicity about it instead. This is one of the key things about these complementary duals that are everywhere, is that that's kind of like the way that it is so. Because the real number system has this subset, we say it is ordered. Ordered means trichotomous in the real numbers, and he's saying because this is a subset of the real numbers that it is so. Not because the real numbers has this subset, but because this subset, this set is a subset of the real numbers. It's points in a point set. That's a quibble of sorts, but it's relevant to reflect on that the different perspectives make it true from all angles. The goal is to find something that cannot have an illusion hidden inside it, that cannot have a trick of perspective or projection hidden inside of it. That's the goal of this completeness in all the things. So we use this property of order when we associate the real numbers with the real line. If A is not in P and A is not 0, then we say A is negative. It can be proved that the real number system is ordered. Moreover, it can be shown by means of the definition of multiplication of real numbers that if A and B are negative, then AB is positive. Then if A is positive and B is negative, then AB is negative. Of course, a product of two or more real numbers is 0 if and only if at least one of the numbers is 0. If A is positive, we write A greater than 0. So the greater than and less than signs are kind of from something named Harriot. They were the first person to introduce these signs, or that's where they came from, the notation, the greater than less than signs. Kind of like the infinity symbol is named after Wallace's lemniscate. Now, the point I want to make about this is that about proving that the real number system is ordered, is earlier we were talking about Euclid's smooth plane and Poincaré's rough plane. What is Poincaré's rough plane? Well, it's the plane, but it's kind of dimpled everywhere. And so does that mean it's not smooth and not continuous? Well, no, it's just kind of like always, it's only flat on the average everywhere. And it's the basis and root of this kind of like, well, what would happen if discontinuous functions became continuous and flat and smooth? Well, it would be Poincaré rough right before it was smooth in terms of all that together, this signal. And so it's kind of considered the signal continuities plane. So in the trichotomy, there's this notion of the real numbers kind of have this vague fugue. And what is a fugue? It's like musical notes that kind of go up and down, kind of like Flight of the Bumblebee or something like that, but hopefully something a little bit more easy to hear. And then what this fugue, and then the vague fugue is that, yeah, they're ordered. The numbers are ordered. And so when we talk about something like with an attenuation and dissipation, like it's just linear, and then that it reaches a point, then it's done, then there's also whether it has hysteresis or ringing or the Gibbs phenomenon right there. Whether that's so, then that's still ordered, that it's all ordered over time. The notion that it isn't is that if it isn't, it's only not so at the very, very end, at the very, very faintest difference. It's not like it's out of order. It's like, well, 7's over there. No. It's all ordered, and then in the elementary degeneracy or the deconstructive account where it's not ordered, I call it a vague fugue. Fugue, like a toccata or a fugue. Anyways, that's just the point to make about it. It's kind of like Poincaré's rough plane are these the vague fugue of the infinitesimals in the ordered reals. It's important when picking names for things in mathematics that they kind of have the same meaning as other words, because they're ordered. The algebraic operations of addition and multiplication have geometric interpretations in the real line. Addition is often thought of as corresponding to a translation or shifting of the real line. Let us assume that the real line is horizontal as we look in our mind's eye. Then in order to perform the addition of operation by 4, we slide the real line to the right 4 units. So he's implementing a mental model as like a slide rule, as we discussed the other day. And he's describing a mental model of this. And so he might be using that later to help establish what these things are. Now that's all what I'm about going to read today. And so we made it to page 8. And so the preface took up the first 5 pages. Page 7 was page 1. And there was described real numbers in the real number line. And there's described that they're ordered. And they're described a greater than 0 if a is positive. And so that is where we got up. And then he's talking about the algebraic operations of addition and multiplication. They're arithmetic operations, and that they happen to so be algebraic operations is because we've also attached an algebraic description to this thing. Algebra and arithmetic are 2 separate things, but they're closed in the finite. So anyways, I'll have to get more to reading about the geometric, harmonic, and arithmetic means in the continuous vis-a-vis the mean, median, and mode in the discrete some more later. Well, I hope this has found you well today, and to carry on, I'll carry on a little bit more later and see how things go. Good luck.